Sandeep, you're able to hear me, right?
Yes.
Okay, okay. Let's start the session. Okay. So you're able to see my screen, right?
Yes. Yes, madam.
Okay. Okay, let's get on to the session. So I welcome you all for the week 3 live interactive session for the course Polymer Concepts, Properties, Uses and Sustainability. So as usual, we'll get on to the brief recap of the lectures of week 3. So lectures of week 3 was on molecular arrangements and states of polymers, right? Yeah. So the lecture 16 was on the aspect of sustainability. So it was on structures in biopolymers. So different biopolymers, they were discussed. Their different structural levels were discussed. Do you remember what are the structural level discussed for the biopolymers in lecture 16?
Yeah, maybe the alpha helix and the beta sheets like these things.
Okay, okay, that is one of the structural levels. I'm saying
Okay.
the major structural levels. It was primary, secondary, tertiary, and quaternary,
Oh,
right?
okay. Okay.
Yeah,
Yeah.
yeah. So these structural levels were discussed, and then polynucleic acid was discussed in detail, where DNA as a molecule for engineering. So here, yeah, it happens. The automated synthesis process happens right through polymerase chain reaction, right?
Okay.
Because of the hydrogen mediated interaction, right? So and then the flexibility, the lack of molecular flexibility due to double stranded DNA was discussed, right? And the controlled length, the rigidity can be controlled, it was discussed for polynucleic acid. And then there was discussion on proteins where the discussion was on cousin, right? The hierarchical structure of cousin. In hierarchical structure of cousin only we discussed on so there was a discussion on alpha helix, as you said, beta sheets and all. So casein is a protein from milk, right?
Yes.
Yes, and it was also discussed that it can be used as an adhesive in transformer insulation boards, right? So between the cellulose, it helps in bonding between the cellulose because of its hydrophilic nature and the hydrophobic nature. It plays a role in because of by interacting with the transformer oil, right?
Yes.
Yes. So there is one more student joining, I guess. Yes. Nishach. Welcome, Nishach. We have just started discussing on the recap of lectures of week 3. Okay. Right. And then polysaccharides were discussed. The complex structure of the pectin was discussed. What are the different type of interactions in pectin was all discussed. Right. Next, lecture 17. It was on concepts concepts of amorphous and crystalline states in polymers, right? So the discussion was from liquid to solid state, right? Uh, right. The disordered state is more of an amorphous state. So in crystalline state, there is a order, that is getting involved, right? Right. The semi-crystalline nature of
Yeah.
polymers. So polymers cannot be 100% crystalline because of their I know large molecule, right? So they are semi-crystalline only, right? And then they the crystallization in atomic systems where this it goes as from the melt you get into nucleation and then the growth. So you have single crystal and polycrystalline systems. Whereas in polymers you cannot get into single crystal, so it will be polycrystalline system only. Whereas you get into an amorphous state when you are quenching from melt, correct? So obviously for getting into crystalline state, you have to cool it slowly. Correct? Are you there?
Yes, madam.
Yes,
Yes.
Yes.
And then there was a discussion on the protein crystallization. What are the complexities involved in protein crystallization, right? I
Yes.
think some music is coming. Maybe you can just keep on mute, right? Crystallization in atomic systems and then macromolecular molecules in crystalline form was discussed. What are the crystals observed in case of protein was discussed, right? And then the rate of crystallization is strongly influenced by the condition of crystallization is also discussed. And then different crystallization, crystallization by annealing, and then getting down by the saturation temperature, bringing it below the saturation temperature, the slow cooling and all was discussed, right? And then what are the influencing factors for forming crystals in proteins? So the concentration of macromolecule, pH, ionic strength, temperature, additives, pressure, mechanical aspects, all these come into picture. And one more thing is that in case of these proteins, the degree of hydration is greater, right? And it is because of this degree of hydration, they are very fragile, right? And you get lot of mechanical advantages when you are having semicrystalline polymers. And then what is the polycrystalline state of the polymers? So you, from a disordered systems, you start forming lamella, and then the sheets are formed, from where you form spherulites, right? And then your polycrystalline state of polymers are formed, correct? And then how do you
Yes, madam.
estimate the crystallinity? Using a DSC you can estimate, right? And then using X-ray diffraction also you can estimate, right, the degree of crystallinity, correct? These were all discussed in lecture 17. Next, lecture 18. Lecture 18 was again on amorphous and crystalline states of polymers, and then thermodynamic description of crystallization and melting was discussed. So this is a first order transition, right? And the kinetics of crystallization plays a very vital role also, right, in polymers, correct? The melting temperature, uh, what happens, beyond a certain temperature, your Gibbs free energy for solid state is lower than that of the liquid state, and that is why you start forming crystals, correct? And what are the complexities involved in polymer crystallization, right? These were all discussed. And then inherent kinetic factors, rate of crystallization, and then mixture of polymers, right? Different aspects, your surface energy once the nucleus starts forming. So these aspects are all discussed. And then the effect of diluent. The lecture 19 was on molecular orientation. It was on uses. So orientation and the quantitative measurements, right? So what are the aspects of orientation in case of molecules, crystallites, domains? Domains comes in when there is a mixture of polymers, right? And then the orientation of the fibers in case of composites, right? And then there was discussion on the average orientation factor, right? How that is how you help you quantify it. And then what are the applications? Like in your biaxially oriented films, for example, in BOPP, right? Where the properties actually differs in different direction, correct? Because of the orientation, right? Because of the stretching in both the directions, biaxially oriented, no? Stretching in both the directions, so your properties also vary, correct? And then your ultra high molecular weight, polyethylene. So we could see that the tensile strength goes up to 3000 megapascals in ultra high molecular weight polyethylene because of the orientation, which is as comparable as aramid graphite, right? And then orientation during processing, the concept of draw ratio, stretching of sheets on rollers, blow molding, right? In blow molding, insert a plunger, right, for stretching, correct? And then injection molding. So these were all discussed, right? And then the lecture 20 was on interactions. So interaction of polymers at molecular level, right? And then non-covalent interactions or non-bonded interactions like your van der Waals interaction, hydrogen bonding, electrostatic interaction, polar and dipole-dipole interaction. And then based on the interaction, you have the hard sphere model, and then square well, Lennard-Jones potential were all discussed. And then interactions in polymers, the coarse grained level or empirical level approach. right? Where your steric repulsion, and in case of there was a discussion on the polymer solution, and in concentrated solution where the entanglement plays a role, and then the concept of intrinsic viscosity was discussed, right? Solubility parameter were all discussed in the lecture 20 on interactions. Lecture 21 was on kinetics of crystallization. So a brief introduction on the glass transition and melting, and then polymer crystallization. The structure and growth, right, was discussed. Correct? Are you all there? Hello?
Yes, ma'am.
Yeah, you're able to recollect all these? You're able to recollect all these?
Yes, madam.
Yeah, okay. So, and then you could remember the plot of the crystallization rate versus temperature, where you could find that the crystallization rate is higher in particular range only. It is you know it increases from as you move far away from your melting temperature, and similarly as you move away from your glass transition temperature. So in between there is a increase, right? Inverted parabola kind of image you would you would have seen in the uh, lecture, correct? And then the fraction of fraction of crystallinity, right? And then
Yes,
the
madam.
Abrami model, Ozawa model were all discussed. And then the final lecture of the week was on introduction to glass transition. So more information on your amorphous state, because your glassy state is an amorphous state, right? Was discussed, and the properties in glassy states, and the TG, the glass transition temperature depends on the history also, right? And what happens in glass to rubber transition, the dilatometry, the importance of glass transition were all discussed in the lecture 22. Okay, now let's get on to the practice assignment questions. The enthalpy of fusion for a polymer is found to decrease from 135.6 joule per gram to 120 joule per gram after 5 years of use. Okay. So if the enthalpy of fusion of the same polymer with 100% crystallinity is 290 joule per gram, then the loss of crystallinity after 5 years is, what is the loss of crystallinity? This is a GATE 2022 question. So any thoughts about that? Was it covered in the lecture? This concept? Do you remember?
I think, madam, the equation of this heat required for melting the can we use these things? The the heat of fusion of polymer crystal multiplied by degree of crystallinity.
Yes,
And,
yes, 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 you are right. Yes, we have to use that only. So how it goes is that, so what are the information given? They have given heat of fusion of polymer crystal, which is 290 joule per gram. And then they have given heat of fusion of polymer at some particular point of time, right? That is 135.6 joule per gram. So we don't know what is the crystallinity in this polymer at time uh, t1 given. Okay, and then they have given heat of fusion of polymer at time t2, which is after 5 years of use. So the heat of fusion has decreased from 135.6 to 120, right? Now we have to find out what is the degree of crystallinity, or what is the loss of crystallinity. So as you said, you can relate the degree of crystallinity with the heat of fusion. So heat of fusion of the polymer is equal to heat of fusion of polymer crystal. If heat of fusion of polymer crystal is nothing but the heat of fusion of polymer with 100% crystallinity multiplied by the degree of crystallinity will give you what is the heat of fusion of the polymer. So from here you can just rearrange and find out what is the degree of crystallinity, right? Xc is equal to delta Hf by delta Hfc. So change in degree of crystallinity or loss of crystallinity after 5 years, we can give it as Xc is equal to delta HF1 minus delta HF2 divided by delta HFC. So you have the value. So Xc is 135.6 minus 120 divided by 290, that will give you 0.053, which is nothing but 5.37% loss in crystallinity. Right? In 5 years, there is a loss in crystallinity of nearly 5%. Okay. So this we can also solve in other form. As you said, straight away you can find out what is the crystallinity at initial when the heat of fusion was 135. So by just incorporating the values of HF and HFC in this. So you can find XC1 is 135.6 by 290. So that is 46.76% of crystallinity. So initially it was having 46.7% of crystallinity, and after 5 years, when the heat of fusion became 120, the percentage crystallinity reduced to 41.38%. So the loss of crystallinity, again you can just subtract the initial crystallinity minus the final crystallinity, which will give you approximately 5.38%. Okay, you're clear, both of you, Nishaj and Sandeep?
Yes, madam.
Yes, yes, ma'am.
Okay. Okay. Next question. Polymer crystals show a range of melting points in contrast to single melting point of crystals of small molecule. Is it because there is an absence of intermolecular interaction, or there is an absence of long range ordering? The polymer chains are not in thermodynamic equilibrium in metastable state, or the melting behavior of polymer crystals is independent of sample thermal history. Which of these is the reason for polymer crystal having a range of melting points? So this is again a GATE 2021 question. Any thoughts about this? Or you want to make a try? Just make a try.
I think long range ordering there is absence of because of entanglement.
Is it that? Or any other option, anyone else is having?
I don't know directly, but according to my thought, it is something like polymer crystal. When the polymer crystal is formed, the crystals are not in the uniform shape because it's having different means the final structures. Perlite is the size is different, so that may be one of the reason due to the difference in the molecular weight.
Okay, so I got two different options. So let me say what is the right answer. It is actually the polymer chains are not in thermodynamic equilibrium in a metastable state. When they are, brought down, they are not in thermodynamic equilibrium. And that is why you have because of the, the structural, complexity. So that is why you have a long range order. Sorry, that is why you have a range of melting points and not a single melting point. Okay. And I think Nishesh, what you were saying is that you form different crystals. So this polycrystalline nature, it is not only a nature of polymers, but even in other materials you tend to form crystals, polycrystalline, material, and that is why you come into the concepts of grains and grain boundaries and all. Right, even you would have heard it in nanoparticles. When you come into nanoparticles, they are polycrystalline in nature and all. You would have come across. So it's not just pertain to your polymers. Okay, hope you're clear. Are you both clear?
Yes, madam.
Okay.
Yes.
Okay, now just let's move to the question number 3. Melt processing temperature of a semi-crystalline thermoplastic polymer is between glass transition and melting temperature, or equal to melting temperature, or lower than melting temperature, or higher than melting temperature. So at what?
Higher than melting temperature.
Are you sure?
Higher.
Uh, Madam, I cannot see the slide.
You are not able to see the slides.
I see
Nishit,
the
Nishit, are you able to see the slides?
yeah right
Yes,
now
I still able to see the
yeah
slide.
right now is okay. Right now is okay.
Okay, okay, okay. That's good.
Melt processing is always higher the melting temperature. It's 20 or 30 degree higher now.
Yes, you are right. It should be higher than your melting temperature. That then only it should be more than melting temperature. Not only for polymers, but any material. If you're going to process as a melt, a solid material you're going to process as a melt, obviously the temperature should be higher than your melting temperature. So it is right. Okay. Now let's go on to the next question. Viscosity measurements were performed for a set of PMMA solutions of different concentration in toluene at 25 degrees. The plot of reduced viscosity against concentration of the PMMA solutions produced an intercept of 21 centimeter cube per gram on the ordinate at C equal to 0. The value of viscosity average molecular weight of PMMA in toluene at 25 degrees is, they have also given Mark-Having constant K equal to 7.5 into 10 power minus 3 centimeter cube per gram, and A equal to 0.72 for PMMA in toluene at 25 degrees centigrade. So this is again a GATE question, GATE 2020 question. So what they have asked? They have asked for viscosity average molecular weight. Correct? And then what else they have given? And what should we use here to find the viscosity average molecular weight?
I forgot. The equation is something like viscosity is equal to K into m raised to n or something now.
Okay. Yes. So what is that equation called?
That is not viscosity average. It is that is apparent viscosity or something.
Actually, the name of the equation is there in the question itself.
Yeah, that is Markov-Haven's equation.
Yes, Markovin's equation. So Markovin's equation is based on your, intrinsic viscosity, and then you find
I,
out your viscosity average molecular weight. Okay.
so intrinsic viscosity is directly viscosity average.
Yeah, you get into the viscosity average molecular weight because you see here the intrinsic viscosity is nothing but your viscosity at concentration, close to zero, and that is what is
Close.
actually given in the question, and that is what is the crux in the question. They have not given us directly your intrinsic viscosity. I think Sandeep, you're also getting what I'm telling, right? So they have not given directly the intrinsic viscosity. Your intrinsic viscosity is nothing but in viscosity at a concentration of polymer closer to zero. That means a bit of polymer you add, what is the viscosity change, right? So they have not given it directly, but they have given that they have plotted the reduced viscosity against concentration. Okay, and then they have found out the intercept at concentration C equal to 0, and the intercept is 21. Okay, this is what is your intrinsic viscosity. Okay, so now your Mark-Having equation is eta equal to kmh into uh, you know uh, your molecular weight raised to the power of a, right? So they have given all. So you have the viscosity, intrinsic viscosity as 21. You also have the value of k, and then you also have the value of a, and then substituting it, you will get the molecular weight. So so 21 is equal to 7.5 into 10 power minus 3 into m raised to power 0.72. So if you rearrange it, so your molecular weight is 21 by 7.5 into 10 power minus 3 whole power 1 by 0.72. So you end up with your molecular weight as 61,366, sorry, 336.57 gram per mole. Hope you all got it.
Yes,
Is it
madam.
is it fine? Yeah. Okay. Now let's proceed. Next question. The density of polyethylene crystals is 998 kilogram per meter cube, and that of totally amorphous polyethylene is 886 kilogram per meter cube. If the density of polyethylene sample is 949 kilogram per meter cube, the crystallinity volume fraction is dash. So how do you find this? This is again a GATE question, GATE 2017 question. So what are the information given, and what is it you are going to find, and how are you going to find?
I
So
think for this problem we can use the equation of this density of a semi-crystalline polymer. That is density of rho is equal to amorphous density multiplied by 1 minus crystallinity, maybe, yeah, plus uh, density of the uh, crystal in multiplied by the volume fraction crystallinity. Yeah, so from here we can get the phi c, the
okay,
crystallinity volume fraction.
okay, good, good. Now let's do it. So as you said, they have given. So this is the formula. So your crystalline volume fraction, you can find it out from the this equation, rho minus rho a by rho c minus rho a, where rho is the density of the sample or the density of the polymer, and rho a is density of the totally amorphous polymer, and rho c is the density of the 100% crystalline polymer. So from this you can just incorporate. So they we already have the information on density of polyethylene crystal they have given. So rho c is given as 998, and then amorphous polyethylene is also given as 886, and then density of polyethylene sample is also given as 949. Now just someone calculate and tell me what is the uh, crystalline volume fraction. Any of you, at least, just substitute the value and tell me what is the crystalline volume fraction.
uh, 0.56 or 56%,
Okay,
56.25.
okay. Yes, it is 56.25%. Okay, this is again a simple, straightforward problem. Next question. Stretching of rubber leads to dash. Decrease in alignment of polymer chain, increase in alignment of polymer chains, no change in alignment of polymer chain, or decrease in strength of rubber. So what does stretching of rubber leads to? So when you
Increase in alignment of polymer chain.
so both
Yes,
of you
madam.
agree?
Yes.
Yes, it is increase in alignment of polymer chain. So as you stretch, there is an increase in alignment. Okay, the alignment increases in the stretching direction. Okay.
So, madam, can I ask? So, this stretching needs to be done during the processing of this rubber, or after the, means when we make this rubber like in the mold, we need to
Okay.
do at the same time. Just we put like in casting in the, then we also need to stretching at the same time, or after the processing we need to stretch.
See, it depends on your application, and how do you get your material also. Okay. So this can be done in either way as well. Maybe if you just get into the processing, rubber processing, then you will really get to know, where they're actually doing it. But this can be done in either way, because in some cases, you will get some rubber sheets. So after which you have to really, do the post processing of stretching it to bring it to particular alignment for some to achieve some particular property, or else during the melt processing itself, or when you're initially processing the rubber itself before cross linking and all those things, you can stretch and bring it to some particular chain alignment, and then you can do the further processing. Okay.
Okay, madam.
Yeah. uh, is it fine?
Okay, madam. Yes.
Yeah, okay, fine. Now let's get on to next question. Structures like helical, pleated macromolecules comes under dash structural levels of biopolymers. Does it come under primary or secondary or tertiary or quaternary? Which structural level it comes of biopolymers. So we, while discussing, the recap, we were discussing on primary, secondary, tertiary, and quaternary levels, right? So under which, levels you get these? I also said you were saying helical, beta sheets and all, right? I told actually the answer in the brief recap itself for this question. Do you remember?
No, madam.
Okay, it's actually your secondary. Your primary is your backbone, your CC, interactions and all those things. Then it starts, turning into some structures like alpha helix, beta helix, or some pleated structure or beta sheets and all. And then goes your tertiary and quaternary, further interactions, intermolecular interactions, some cross linking and all, forming a 3D network structure, and then further entangling and all will come under tertiary and quaternary structures. Okay, hope you got it. Right, now let's move on to next question. Under the complexities of crystallization of polymers discussed, now you have to identify the correctness of the below statement. The actual melting temperature of a macromolecule is greater than the equilibrium melting temperature. Is it true? So there was a discussion on complexities of crystallization in polymers, right? In amorphous and crystalline polymer, lecture 18 and 19.
Yes.
So,
Uh, I think yes, the statement is false.
so both of you agree with that? Is Nishaj there? Do you also agree that the actual melting temperature is greater than equilibrium melting temperature is false?
Actual melting temperature is greater than the melting temperature. It is true.
Is it true? Your actual melting temperature is greater than. Okay, let's see what is the answer. It's actually incorrect. Your actual melting temperature is less than your equilibrium melting temperature. Equilibrium melting temperature, that is why you have that infinity, right? That
So
is your
okay, okay,
equilibrium.
agreed. But my question is that in DSC, which melting point is we are getting?
Your actual melting point that you
Actually,
are
no.
getting. Yes, yes.
Yes,
Because
yes,
this
yes.
is,
Actual melting point is
yeah,
less
your
than. Okay, okay,
equilibrium
right.
melting
Okay, okay.
temperature you calculate it thermodynamically, right? With your
Yes, I understand. Now
enthalpic
I
and
understand.
yeah. So this is what is the relation, right?
Correct.
So your effect of your interface, and then your diluent, all these come into picture, and the macromolecular nature itself, it brings in picture your surface energy, right? So because of all these parameters, your actual melting temperature will be less than your equilibrium melting temperature. Okay, sorry, I think hope you would have seen the answer also. Anyway, let's see the question. Anisotropy in refractive index due to orientation is referred to as, is it referred to as scattering, or is it referred to as birefringence, or is it referred to as poling, or is it referred to as stretching? What is it called? Anisotropy in refractive index due to orientation. I showed the answer also.
Oh, actually, I can't see.
Okay,
uh,
then it's good. Then it's good. So tell me what
that
is.
from that professor mentioned that due to the stretching there is anisotropy happens, and we can characterization this orientation by using this bifringes.
Yes, it's
So I think
birefringence.
yes.
Yes, yes, it is birefringence. because of the anisotropic nature, your refractive index in in the different directions will be different. So this phenomenon is called as birefringence. Okay, and this is a measure of the orientation. Okay, now the range of charge interaction is, what is the range of, so in non-bonded interactions, there was a discussion on charge interaction, uh, different interactions like repulsive interaction,
Yeah,
dispersive interaction, and all these things. So it was all having range with respect to the distance between the interacting component or atoms. So what was that range for charge interaction?
I think this
It
one
is it 1
option
by
A.
r or 1 by r power 12 or 1 by r square or 1 by r power 6? Which is the right answer for this?
Yes, 1/r.
1 by r. Are you sure? Both of you?
I don't know.
Okay, okay, no issues. It is 1 by r as you said. So 1 by r power 12 will come for repulsive interaction. Okay. So for charge interaction, it is 1 by r. So there are also other interactions like charge dipole interaction where the range is 1 by r square. Dipole is 1 by r cube. Right? Charge induced dipole is 1 by r power 4. Dispersion interaction is 1 by r power 6. And the repulsion is 1 by r power 12. Okay? Next question. Identify the crystallization model from the below statements. The ratio of crystallinity as a function of time. Which model describes the ratio of crystallinity as a function of time. And then which model describes crystallization based on cooling rate. So the options are whether both are described in Abrami model or both are described in Ozawa model, or whether the ratio of crystallinity as a function of time is described in Ozawa and crystallization based on cooling rate is described in Abrami, or is it vice versa? That is, the ratio of crystallinity as a function of time is described in Abrami and crystallization based on cooling rate is described in Ozawa. Which of these is right?
Uh, Option 3, Aframi for A and Ozawa for B.
Okay, you are right. So it is option 3. Yes, the ratio of crystallinity as a function of time is described in Abrami model, and your crystallization based on cooling rate is described in Ozawa model. Ozawa model is in fact based on the dynamic crystallization, right? So this is how it is. So Abrami model for isothermal crystallization, and your phi c by phi c infinity is 1 minus exponential of minus KV, which is again a rate constant, t power n, where again n is an exponent. And Ozawa model is for dynamic crystallization, as I told. So phi c by phi c infinity is 1 minus exponential of 1 minus k oz, which is oz describes Ozawa, which is again a rate constant, and t dot raised to the power n oz. So where t dot is your cooling rate, right? So what happens if the cooling rate is very fast? What happens for a very high cooling rate?
Amorphous.
Yes.
Yes,
Also,
yes,
the time also increase. More time is needed
yes.
to
So the cooling
reach
rate
the.
is very fast. As I said, what happens to this equation is that the value of exponential term becomes 1 because the denominator becomes very high. That means the overall term is exponential of 0. It becomes. So that is nothing but 1. So 1 minus 1 is 0. That means there is no crystallinity and it is only amorphous system that is being formed. Okay. Now, next question. Identify the glass and rubbery region in the below figure. So, this is the figure. So, identify. So, there are 2 regions. One region is this one where the volume decreases, The slope of volume decrease is high, and the other region where the slope of volume decrease is low. So which of these signifies glassy and rubbery region? And what is separating these two region? From the figure itself, you can say what is separating the glassy and rubbery region. Which point
TG,
there is a? Huh?
TG.
Yes,
TG.
yes. Your glass
So
transition is
above TG is a rubber,
okay.
below TG is a glass.
Yes. So above TG, it is rubbery region. Your volume changes are higher, and below TG there is a glassy region where your volume changes, is lower. Okay. Okay. This is how it is, and that's it with the questions. Now, any doubts?
I have, madam, two doubts actually.
Yeah, yeah. Tell me.
In the lecture 17, the professor mentioned that we can measure the crystallinity by using the DSC method. So, can you explain a little bit more this?
See, what do you observe in DSC is that there is a, it is actually differential scanning calorimetry. So what do you do is that you place a reference sample and your test sample, and then you give heat flow and, to both the samples, and changes, difference between these is captured. The reference and the reference will be mostly an empty pan. And what happens is that during DSC, the changes happening in the system due to this temperature is captured, and what happens is that the material, it will undergo different transitions. For example, if it is having some crystalline phases and all, no, you will be able to see peaks. For example, your uh, you will have a in a, so there is a phase transition, and this is a heat flow. Obviously you will find out the enthalpy of crystallization. In enthalpy of crystallization is it an endothermic or exothermic process?
Enthalpy of crystallization.
Yes. So it is a exothermic process. So there is a heat liberation. So you will find a upper hill, or kind of some inverted parabola, you can just imagine. Okay.
Yeah,
Okay, so from that, you can find out what, you have the, relation with, again you will also find the melting or the fusion curve, which is an endothermic curve. Okay. Which is kind of a lower V shaped hill. Okay, I think you're able to see my this one. So with these, you can find out, you have the relation with these enthalpies and your degree of crystallinity. From these, you can just back calculate it.
you mean that we need to equation of this, like heat required for melting polymer is equal to heat of fusion of polymer crystal
Yes,
multiplied by
you will have relations. Yes, yes, yes. You will have to use the relations. You will get the data from which you will find out, the area under the curve will give you your heat of fusion and heat of crystallization and all. The enthalpy of fusion and crystallization and all. From that, you will have to back calculate what is the crystallinity.
Okay. So
In
for that,
any measurement technique, there will be, a parameter which can be uh, uh, you know found out by the instrument, and then there will be, a parameter you have to back calculate it. Okay. That is how it goes.
okay. So madam, for this scenario, we need to know the polymer. What is the polymer? Because sometimes we do some unknown material. So
Yes.
in that case, how?
You see again, you may not know. No, it's not necessary that you should know. You can find out, you get to know the values of this one, your heat of fusion and
Yeah,
heat of this one, and then you can back calculate. But still, it cannot be, like totally blind. You may have some information that you may predict that, this might be a combination of these polymers, and then you can just, for example, a polymer composite means you will know get to know what will where the curve will appear for
Okay.
a
So,
polymer A
oh,
and
I
a
understand. So you mean that we first need to go like FTIR to
yes,
know
yes,
the,
yes, yes, yes.
yeah.
Your
Then
chemical
then if
composition,
you
yes,
go
you
for
will get to.
TSC, it will help you. Okay. Okay.
Yes, yes. Always, in understanding, unknown polymer or working on a new material. Always, you cannot just stick on one analysis technique. You will get in, you will be doing multiple techniques, and then combination of those
Okay.
you will get into what is the actual polymer is. So based on this, you will see the transition as glass transition. You can also find out the glass transition temperature. There will be a step in the curve.
Yeah.
Okay. Maybe I can just. Show DSC, how a
Yes.
DSC
Yes.
curve looks. So see, so it may look something like this, right? So this is
Okay.
a, so this curve will mark the glass transition, and then here you
Yeah.
have the cold crystallization, and this shows the melting. So from these, you'll get to know the relationships. You have the temperature information also and the heat flow also. From this you can just back calculate the informations, right?
Yeah. So in that case, madam, we need to do first the heating and then cooling.
Yes,
Then we get the
yes, you do
crystallization.
heating. Yes, see, again, these options are, it depends on the literature. If you just get to understand the material, and you will get to know, how the process should be: first heating followed by cooling, or cooling followed by heating. Sometimes, just a single heating itself will give you the required information. Sometimes, you have to go through cycles, a single cycle of heating and cooling, or sometimes multiple cycles.
Okay.
You will get to know, you will have some more information, additional information on the material. Okay.
So in that case, we should know the basic information that which is a polymer, or this unknown. It is quite difficult, I think.
Yeah,
To
totally unknown material you may
yeah.
not be able to. So first you should
Okay.
have some prior information, at least some basic information, what material, whether it is a polymer or it is, a normal, material, what material it is, some basic information. You will not know that it is exactly, high density polyethylene or low density polyethylene, but you can get to know some basic information on that, and then you can actually delineate what is the exact probable material. Sometimes there will be composites, many cases, it will be
Yeah.
composites or blends
Yeah.
of polymers. So your TG, the step you saw in the image. Sometimes, for example, it is a blend of two polymers, means
Yeah.
the value will be somewhere in between. So you will get to know, okay, it is there in between, and if it is closer to one of the materials, like if two materials, one is having a glass transition of 60 degrees and another one is having glass transition of 120. So you may end up getting the glass transition of the blended material, somewhere in between these two. And whichever is to whichever it is closer. For example, if you get something closer to 110, then that means the polymer 2 is dominating.
Yeah.
If you get something closer to 65, then the polymer 1 is dominating. So those kind of further information you can get. Okay.
Yeah.
Okay.
And for this DSC, uh, madam, for the heating rate, we need to put the heating rate or especially for heating rate. So is it very important to give the correct heating rate or
Yes.
some
Yes.
approximation?
Yes, yes, yes. I mean, see, it depends on the sensitivity of instruments. So, you have to choose the heating rate in two aspects. One is that you shouldn't lose the material information also, and second one is that the sensitivity of the instrument. Sometimes, if you're going for very low rate, you may get lot of fluctuations. That may also,
Okay.
it will not give a proper result what you want, or it will not give a proper information that is needed. Sometimes if the rate is too high, straight away I'm giving like 100 degrees per minute, then you may lose some peak information will be missing. So you will not get, you may feel that okay, it is having only, glass transition, it is not having any crystal phase, but the crystal phase peak will not be, expressed because of the faster rate. So you have to really, understand, you have to understand the material and then give some nominal rate, understand the instrument as well as understand the material also.
Okay.
Okay. Yeah. So any other doubts?
No.
Okay.
Yeah, actually, I is not doubt. Actually, I also professor does not clearly or details mention in that lecture. That is this the phenomena like Hart sphere, square wheel, and another one is Leonard Jones.
Ah, yes.
So is it uh, in detail? Actually, it will be updated in later. The
See,
details discussion.
this course is actually giving, kind of a complete overview of polymers. So it is kind
Okay.
of
Okay.
a introduction to your macromolecules. So if you want,
Okay.
to really know on further, understanding, it may be like, relevant for you to understand the Leonard Jones potential. Okay,
Yeah,
but for some others, it may not be. So you can just go on for further reading. That is why, he mentions the
okay.
references in every, lecture, and also he
Yeah.
has given
Okay.
the book references. So if you want to go on for further, understanding of those aspects and all, you can just go in for further reading. And if you get doubts, that is where you have to make use of the live session, and also,
Okay.
you have
Okay.
to post your question in the forum.
Okay.
Okay,
Okay.
so
Madam.
that,
Okay.
you can get the answers.
Okay.
Okay. Yeah.
Okay. Thank you.
So any other doubts? Any other doubts? Or should we officially close the session for the day?
No, nothing more because this Sandeep is mentioning something about the DSE. My personal question is Sandeep is dealing with this DSE equipment.
Actually, yes, I am just starting with this daily, but I am not expert. So I am also learning. So that's why I have some doubts. So I am asking Madam
Yeah,
regarding
I
that.
understand because we have two DSE from a TA instrument 2000 series.
Hmm.
So what Sandeep, I know you what you are asking about. It's TA. The crystallization is basically the internal parameter is already set is 100% polyethylene. That is what it calculate. Not for all the polymers, you cannot get a 100% crystalline material. So basically the
Yes,
TA
yes.
itself it is they are also mentioning this 100% polyethylene based. So they all the crystallization what they are calculating based on that value, even with other polymers also.
Sorry, can you repeat once again what you mentioned?
See if you are if the crystallization is percentage crystallization, if you want to measure, TA
Yes.
directly give the answer, means the instrument directly give the answer. Okay, it is 40
Okay.
percentage or 45 percentage or 35 percentage. But as we are dealing with the polyethylene, we know that this 100 percentage polyethylene is already there. But if you are dealing with other polymers, it may not be there. This is the thing.
Yeah, actually, for my case, there is some unknown. Maybe it may be some composite also because we do not know. So that's why I am asking for some unknown material. How can we start the process?
Yes, okay. For DSC, you can it's a basic tool, not a means fundamentally to cover all this polymer classification is not at all possible. It's a basic tool to understand whether it is a blend or how many materials are there, how many peaks are there, how many crystallization is there. This type of things you can identify first. Then you have to go with other tools.
Yes. Yes.
That's what I was saying. Not if you're dealing with really unknown materials, you cannot just go with just single analysis technique. You have to go ahead with multiple techniques, and then bring in correlations, and then you find out that okay, this is what is the material, and this is what its behavior is about and all. You cannot just go with a single technique. You have to use multiple techniques. uh, okay, that is what it is.
Yes, yes.
There's something, one more thing I want to add, because normally the DSC is running at 10 degree per minute is the rate normally everybody is giving. If you reduce the rate, you can refine the peaks. Means
Okay.
if you
So,
have doubt that there is two peaks, but it is not clear, then reduce the rate.
okay. So reduce the heating rate is better.
Yeah, it's better.
Not in all cases. That is what I said on the instrument sensitivity. In some cases, there will be limitations where if you go in for very low rates like 1 degree centigrade per minute and all, there you need some sophisticated DSC. You cannot just go ahead with a normal DSC. Where you have to check in and understand the sensitivity of the instrument itself.
Yeah,
As I said,
that's right. Yeah.
in normal 10 degrees or 20 degrees centigrade per minute is followed. So if you have to go for lower rates, you really have to check whether the instrument is sensitive to that or it is just giving noise. So
Yeah,
that
that's very important. But
that
for
is
me, it's working. And one more thing, the sample weight, it's a factor.
yes, yes. You
Sample
cannot go
weight is
for
a
very, your
yeah.
weight should be in milligrams, like maximum, 2 to 5 milligrams it should be.
Yes,
You
yes,
shouldn't have,
yeah.
add too much of sample also. So that will also
And
affect your result.
TA, what TA is mentioning that the flat surface is you have to maintain. There should not be an air gap or something in between this. Lot of other parameters are
Yes,
there,
yes.
practical parameters.
Yes, yes, yes. Once you start using the instrument, you will get to know the in and out of it. And, by doing different samples, different kind of samples, you will get to know, what kind, how to really get good data from a particular instrument.
Yeah, of course. Not only aluminum pans, they have different kind of pans like gold, silver, a lot of platinum,
Yes,
a
yes.
lot of things.
So,
Yeah, it's okay.
anything else? Or,
Yeah, it's wonderful. It's a good class. Actually, I during the week 3 I didn't attend because three
okay,
class I didn't attend. That's why little. But I'll make it, no problem.
okay, okay. Okay, and also please go through the lectures and go through it multiple times. Okay, and also any doubts, please write your questions in the forum as well. In between the week, you may get some doubts while listening to the lecture, but either write down somewhere so that you can ask in the live interactive session, or else you can immediately post in the forum so that you will get reply from the professor as well. Okay,
Okay, okay.
okay.
Sure. We'll do it.
Yes, yes. So make use of the forum, okay, and make use of the live interactive session also. Okay. Yes.
Yeah. Okay, okay.
Okay.
Okay, thank you.
Thank you.
Thank you, madam. Thank you very
Thank
much.
you. We'll have the next class on next Saturday, 4 p.m.
Next
So,
Saturday only.
Yes.
tomorrow,
Hereafter, yeah. Tomorrow there is one more session that is taken by a different PhD scholar. You can attend that session as well. Okay.
Okay, okay.
Tomorrow
okay,
it happens on, so this for this course, polymer concepts, there are two live interactive sessions happening. One session is taken by myself, Kritika. The other session is taken by another PhD scholar called Prabir. So you can attend both these sessions or either of the sessions whenever possible. So my sessions happens on every Saturday 4 to 6 p.m. and Prabir's
Okay,
session
okay.
happens on Sunday 5 to 7 p.m. Okay.
okay, fine.
So
Yes.
he will also discuss about this lecture, week three lecture also,
Yes,
or
yes,
any
yes.
other
Tomorrow
else?
there will be a
Oh,
discussion on week three lectures. Maybe he will discuss some
okay.
different set of problems.
Oh, okay,
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 fine.
Okay.
okay,
Yes.
okay. Thank you. Thank
Yeah. Thank
Thank you very
you.
much.
you. Okay, thank you. Bye.
Thank you. Have a nice weekend.